of the globe to attend this two-day school. So I would actually, unfortunately, our director is supposed to be here, but for some other reasons, he has to go to Pune. So I requested our Dean NSF to say a few words and welcome to this meeting, to the school.
Good morning. So very nice to see you all here. So it's a hearty welcome on behalf of TIFR and also School of Natural Sciences faculty, TIFR, for this 15th school. So here it is on instrumentation for elementary particle physics of ICFA. So I'm extremely happy also to see that TIFR is organizing this meeting, which is second of its kind. The first one was organized about 30 years back here. So TIFR has a great legacy in high energy physics research, starting from our founder director, Dr. Homi Bhabha, who was a leading researcher both in experiment and building experimental facility as well as theory. So from the beginning, so he was doing cosmic ray research, and with time, so this experimental facility spreaded all over the country, starting from the extreme south, Kolar Goldfield, where he built an experiment which is about 3 kilometers below the ground. And also we have experimental facility on Himalayas, which is about 4.3 kilometers high above the sea level. So that institute has grown significantly. Apart from this campus that you see, which we call the main campus, which has slightly more than half of our faculty, we have also centers. So for example, for biology research, there is a center called NCBS in Bangalore. And then we have a theoretical physics research, which is similar like ICTP, we call it ICTS. So that's also located in Bangalore, where theory, particularly with an emphasis on physics, covering almost every areas. So we also organize schools there, and there is a CAM, which is called Center for Applicable Mathematics, which is also located in Bangalore. Then we have NCRA, so where radio astronomy research is done, and also the GMRT facility, which is one of the unique facility in the world. So which got also IEEE recognition recently as a innovation kind of thing. Then recently we have built a center at Hyderabad for interdisciplinary research. Apart from that, we have many field stations. So in this campus, we have 3 schools: School of Mathematics, School of Computer Science, and School of Natural Sciences. So in natural sciences, we have about 7 departments: biology, chemistry, and in physics, there are 5 departments. So the research that we take care of starts from the research of functionality of brain, emotions, health-related issues like drug delivery, then carbon dioxide capture, and so on in chemistry, superconductivity, and then, of course, intense laser field, and so on. So TIFR's uniqueness is that we give a lot of emphasis in building experiments, whether it's a tabletop experiments or big experiments. For example, we have a pelletron here, which is basically a home-built experiment, which caters to a lot of scientists in the country. And as you know, that high energy physics, of course, is one of the leading contributor in the country. So they have participations in L3, D0 experiments, BELE, apart from the LHC participation. And for the LHC activity, we also contribute significantly in computation, because we have a grid computer, which I think takes care of a huge load. We have a ILGTI, which is a supercomputing facility, which is primarily used by the high energy lattice gauge theory people. And in detector building, of course, there is a long legacy also. So I'm sure that you all will have a great time here during the school. Apart from the school things, that if you are interested in any other kind of activity which is going on in this campus, you are welcome, because the labs are very, very welcoming and open to everybody. So you can visit anytime. I hope you will enjoy your time here, because this is Mumbai, you know, I mean, remain usually hot. And of course, monsoon can be little difficult, but this is the best time of Mumbai. So you actually have an extremely good ambience around, and a lot of things are happening. So I hope you'll have time to explore also the surroundings as well as the seashore that we have here. So without taking more time, I welcome you all again, and I hope you have a great time here during the school. Yeah.
Thank you. Thank you, Professor Maiti. Okay. So now I would request our department chair, Professor Guchat, to say a few words.
Hello, good morning, everybody. Nice to see very young kids here. So it's on behalf of the Department of High Energy Physics, it is my pleasure to welcome you all here once again. And indeed, it is a very great and proud moment for us in organizing this school. I think it is the second time we are organizing this school. So we are very thankful to the International Organizing Committee giving us a chance to host this school. And in addition to that, we wish to congratulate also Professor Govindo Majumdar and his team for taking this responsibility to host this school very nicely. You will see the type of arrangements they have made. It is really the fantastic. I believe so. And I understand it. I have seen this. And as you know, the organizing this kind of school is not so easy. Apart from setting up lectures and getting the very good lecture speakers, they need to set up various kind of innovative experiments. I think they have set up about 30 experimental setup they have. And in order to set all these things, one really needs some kind of thought, proper planning, and the huge effort. And I know his team, Govinda and his team, they have been working last couple of months really tirelessly. So I believe we will enjoy this school very much. And already our Dean Professor Maiti said it. Traditionally, our department is very rich as far as high energy physics is concerned. We have started the energy physics activities since the TIFR was established. It's about 74 years ago. So we participated in the accelerator-based physics, non-accelerator-based physics, and also we had the facility for the gravitational experiment. So we have various kind of ongoing activities are going on, including the tier 2. So I welcome you. Whenever you will have time, if you are interested, you just crash the door in the laboratory, our office, you come, we'll be very happy to talk with you. Okay? So I'll not take much time, I'll stop here. Before I stop here, I just wish a very successful, very nice and very enjoyable school. I believe when you will go back, you will go with a very sweet memory. And I believe you will learn a lot. You have to learn it because after all, you are the torch bearer for future high energy physics. Okay? Thank you very much.
Thank you, Professor Guchat. Okay. Before I will take 2 more time our first lectures. Just to say one thing, this is the school 30 years back we had. To just celebrate that, I intentionally decided the same 12th February the school for this school also. This is 1993. This was the 12th February was the school is here in the same lecture room. And that time I was a student. Okay. And other thing I say that people say that this is this founding director Bhabha. And he is the Bhabha whose name you read as a Bhabha scattering. This is the Bhabha. Okay. Now let's come to our school. So this you have seen these lecturers. First lecture will give the Professor Amol Dighe. He is the senior faculty members in our department, in our institute here. He is main field of work in this neutrino physics and also collider physics beyond the standard models and CP violations. Neutrino physics, actually, he is this one of the main person who is theoretically motivated and helping for all the theoretical side for the neutrino, India-based neutrino observatory. And he is also give the very regularly, lecture to the students, not only the scientific community, outside the community. Recently, he told that he gave a lectures where the attendance was the age from 6 to 80. So that kind of level also he gave a lectures. And he is a very good teachers. And recently he was awarded the best teachers in the TIFR graduate course. So I hope is the appropriate that he will start that lectures for this particle physics. Amol.
Hello. Share, no? Yes, sir. Share. बंद कर दो. Hi. Can you hear me at the back? Yeah. So thanks, Govindo, for this kind introduction, and welcome to all of you, all the students and also all the non-students for this ICFA School on Instrumentation. So the organizers told me to talk about landscape, okay, and then I asked Govindo, what does landscape mean? And he said landscape means you draw a portrait of the standard model. Okay, so I've chosen to talk about the landscape of standard model. I understand that most of you would definitely have some familiarity with the standard model, but I will not assume too much because this is the very first lecture of the school. So I will try to go slowly, and depending on your feedback, let us see how much in detail we can go in the next two lectures. This one is tomorrow morning, one is the after tomorrow morning. So again, start with thanking ICFA and TIFR for giving me a chance to talk about this. So before we start this, it's sometimes good to have some idea of what is the final aim, the great aim. Okay? It's not the aim you start with, but the aim that you want to reach finally. Okay? So this is some kind of a sketch that I recently made for some strange document that I was making, which sort of tells you what are the frontier areas in high energy physics that we want to study, that we want to explore. Okay. And whichever things you are doing, whichever analysis you are doing, whichever experiment you are working on, finally your aim will perhaps span one of the areas listed on this. Okay. So just to go through this quickly, so everything is, of course, based around a standard model, and no, we will in this course talk mainly about a standard model. But the standard model covers many areas. Okay, it covers what we normally call as the energy frontier. Energy frontier is the kind of science that we do when we go to higher and higher energies. For example, currently the Large Hadron Collider, and afterwards, of course, we're thinking of building machines which have even higher energy. Okay. Some of that arrow has stayed. Okay. It's okay. Okay. The current hot topic in this, of course, Higgs boson, because we need to find the properties of Higgs boson. And as we'll see in the next couple of lectures, precision measurements of properties of Higgs boson is going to be one of the major aims of what we are going to do next. Okay? Which means that we try to determine what are the Higgs couplings, we try to determine what is the electroweak potential, and we also try to find firstly whether there are any particles beyond the standard model, which are called as BSM particles, and their interactions. So that's something that we aim to do on the energy frontier front. Then we have the intensity frontier, okay, which is in some sense also energy frontier, but approached in a slightly different way. This is the kind of thing that we do in experiments that we call as flavor experiments, flavor physics experiments, or experiments to do with neutrino accelerators. Okay. So here, for example, in the flavor physics experiments, we don't try to go to energies as high as energies of at LHC. So LHC we go to 14 TeV. In the flavor experiments, we are satisfied with about 10 GeV, okay, because all you want to do is produce lots of B mesons, for example. We study CP violation, parity violation, some anomalies that have been very recently observed in various experiments. We study the phenomena of quark mixing as well as neutrino mixing, and we look at electromagnetic dipole moments, of which also you must have heard very recently because there was an anomaly. And of course, we do BSM searches, but these are in an indirect way in the sense that in these experiments, we do not expect to find or create real particles that are beyond a standard model, but we expect that we can measure their effects that come through quantum corrections, okay, or relative corrections or loop corrections, whichever way you want to look at this. Okay. So these two are going to form a large part of my lectures today, tomorrow, and day after. But of course, there are two more frontiers, okay, to which we will not go, but let me just mention them. One is the so-called cosmic frontier, which is where we look at study cosmic rays, we study dark matter, and we look at neutrino astronomy, neutrinos coming from the sky. We also try to look at hypothetical particles, which may exist, may not exist, axions, dark photons, and we believe that dark energy is a real quantity, and we try to determine that. But that is the part of cosmic frontier. And then we have the theory frontier, which is what theories dwell in, and it's my duty to say so because my department here is formally called Department of Theoretical Physics, although I spend a lot of my time in the Department of High Energy Physics. So here we of course study the theory of gravity, grand unification, and some of these areas that also border on the standard model, which is what I work in, which is effective field theories, when you want to describe something that's happening at a high scale, but you do not know exactly what it is. And problems like anomalous gauge couplings. For solving these, you need to do higher order calculations in the standard model itself. Okay. So this is going to be the big picture, but we are going to go to this big picture very slowly in steps. So we are here to study instrumentation. Okay. So basically, to answer all these questions, we are going to develop tools, or we're going to learn how to develop tools. What are the big tools at our disposal right now? Okay. So of course, this is the biggest tool that we have, accelerator-based tools. So at LHC, this is the LHC tunnel, as many of you will be familiar with. That's the way it looks from inside, if you haven't ever been inside there. We have got CMS, where many of my Indian colleagues have been working on. There is also ALICE, the experiment with heavy ions, where many of the Indian colleagues are working on. Then there is ATLAS, and there is LHCb, which are also two of the other experiments going on in this. Okay. So that's our one major tool. Another major tool that we have is the current experiment called BEL2, which is the currently running sort of biggest experiment that studies flavor physics. Okay. So this is the one where we do not go to tens of TeVs, but we go to tens of GeVs. So really, really low energies. However, in spite of that, we are able to find out and probe properties of heavy particles. How do we do that? We'll come to that perhaps in my third lecture. In addition to that, in the field of neutrinos, which is also one of my loves, there are so-called long baseline experiments in which you create neutrino beams by using accelerator. Right? So this is of course the school organized by ICFA, future accelerators. And therefore, I think it is my duty to also mention that even in the case of neutrinos, to find out properties of neutrinos, their masses, mixings, interaction, you are going to need experiments that start with some accelerator. The beam goes here. This is T2K experiment in Japan, where the beam goes underground for about 300 kilometers to reach the target. And this is experiment NOVA in the US, where the beam starts from Fermilab and goes about 800 kilometers to the NOVA detector in Minnesota. These are going to be the future tools that we are going to have. And I just mentioned accelerators, not the experiments. This is possibly what we will have in a few decades, the future circular collider at CERN. So this is the current LHC size, and the plan is perhaps to have something which has a circular circumference of about 100 kilometers. Then this is an experiment which is currently in process. We are not sure of whether it will happen or not, but that's our hope, which is an international linear collider at Japan. And this is really large. This size shows you the size of a football field. So you can sort of imagine how many fields will fill this machine. And for neutrinos, we plan to have the deep underground neutrino experiment, June in USA. Again, you produce a beam at an accelerator in the Fermilab, and you pass that to the Sanford Underground Research Facility. Okay. So these are things that we are going to have. But of course, in order to be able to make these and use this, we have to start from the very basics. Okay. So now we are going to come back to very, very basics, because somebody some time back said that if we start at the very beginning, it happens to be a very good way to start. Okay. So what will I cover? I will try to talk about these three topics. In this lecture, I talk about historical development of the standard model. Perhaps all of you are aware of this. Okay. And in fact, among the senior people, I'll be very happy to get corrections to whether I got some historical aspects wrong. But I really chose to do this because, again, this is a school of instrumentation. And you realize that over the last century, the tools that we have been using for discovering particles have been changing. Okay. By tools, I do not only mean experimental tools, which of course we will talk about, but also mean theoretical tools. We didn't have quantum mechanics when we started in 1900. That's where I'm going to start with. Now we have, of course, quantum mechanics, we have relativity, we have relativistic quantum mechanics, we have quantum field theory, and then we have standard model. So I try to sketch how over the last century and a half or so, the tools, the particles, as well as the theories of how we understand elementary particle physics kept on developing. In tomorrow's lecture, I will talk about the theoretical formulation of the standard model. So talk about how interactions and symmetries tell us about how particles behave in a nice way. And in the third lecture, I will talk about experimental tests of the standard model. Okay. So of course, it's a very vast canvas to cover, but I will try to do as much as you can. You are very free to sort of stop me in the middle and ask questions, okay, even if things are not clear. You are also very welcome to find me after the lecture during tea breaks and so on, because as I said, everything can't be covered here. So we can talk during tea breaks and maybe get some clarification. Okay. As we said, we start at the very, very beginning. Okay. And that beginning is almost 125 years ago, which was in 1897, when J.J. Thomson discovered the electron. Essentially, he discovered that if you look at what at that point were called cathode rays, happened to have a same value of E over M, okay, and which was measured to be about 10 power 8 coulombs per gram. This was 1897. He got Nobel Prize in 1906. There are going to be so many Nobel Prizes in this, as you know, that I will just put their pictures and not really talk about it. The next step here was in 1910, when Millikan did his oil drop experiment. And at that time, the value of electric charge was found to be about 1.6 times 10 power minus 19 coulombs. Okay. So we now have electrons. Next step would be the so-called Rutherford experiment, although he didn't perform it, but no, he was the one who proposed it. So it is, of course, known by his name. we had alpha particle source moving towards a gold foil, and looked at scattering of the alpha particles. Most of them went straight. Some of them deviated by much more angle than we expected. And this perhaps all of us have studied in our high school physics classes, that this led to the discovery of nucleus. So this observation was consistent with not with the kind of Thomson model where everything is equally distributed, but having a very heavy nucleus in the center and electrons surrounding that in a very, very rare crowd. Okay. Around 1930s came the hypothesis of the neutrino. Okay. So nuclear reactions were seen. Beta decay, as all of you are familiar with, was observed. It was in the beta decay, you found a daughter nucleus and an electron. Since it's a two-particle decay, as it was thought of, it means that the energy of final electron would be fixed. And if you plot the number of electrons as a function of the energy of the electron, essentially you would expect to find the spectrum, which means that energy has only one constant value. Okay. So what was found that indeed actual spectrum looked like this, which was inconsistent with just having a two-particle decay. And therefore, Pauli in 1930 proposed that there should be a new particle, it's called neutrino, which we do not observe. I don't know how many of you know the story. These days, we theorists postulate one particle for every anomaly that we see. This was, of course, observed in many nuclear beta experiments. Pauli, of course, was brave enough to propose this, but he was not brave enough to go to the conference to say it in front of people. So he actually has written a note called Meine radioactive Herren und Damen. So my radioactive friends, he sent a letter saying, I think there is a particle which is not detected. But I have to go to my village for some party, so I cannot come to this conference. Please be. Okay. Theorists have become much more brave since then. Okay. To mention that, I call it hypothesis. I do not call it a discovery, where nobody calls it a discovery, because discovery is only when you actually see the particle, no? Even indirectly, but you have to see it in an experiment. And that's the reason it's important for us to build equipment that can confirm the nature of particles. Okay, hypothesis is not enough. In about 1932, Chadwick did this experiment in which he had a polonium source which gave alpha particles. This was known. These alpha particles were absorbed in a beryllium target. And if you put a detector here, you basically would see nothing. Okay, so we do not know whether there is something here because detector gives you nothing. But when he put a paraffin wax target just after this, protons were created. And that told us that there was something here which you did not observe, but which, when it hit paraffin wax, created protons. And of course, these were neutrons, and neutrons were not discovered easily in the detector that are sensitive mainly to charged particles. Okay? Whereas in paraffin wax, the neutrons underwent some interaction, charge current interaction, which gave them protons. And protons are, of course, charged, so you found them in his measuring apparatus. Okay, so that's about 1932. Around the same time, the first antiparticle was found, okay, which was the positron. This is a cloud chamber experiment. Very nice instrumentation here. So this is actually a lead plate, and the positron actually travels from here and comes out at this end. And the fact that it has deviated towards the left in the magnetic field tells you that it has a positive charge and not a negative charge as an electron. Okay. Now, one question that you may think of this is why it could have been electron traveling like this, and therefore that would travel towards right, not towards left. Okay. But that was prevented by having this nice lead plate, and the particle would lose energy in lead plate. Okay. If you lose energy, then what happens? Your speed decreases and you turn faster. Okay. So therefore, looking at the curvature up and curvature down, you realize where the particle came from. nice trick to realize whether it's upward moving or downward moving particle. Okay? And as you clearly see, this is a fast particle because curvature is less. This is a slow particle since curvature is more, which means that the particle actually went from here to here. Okay? Magnetic field direction was known. No, so F is equal to V cross B kind of thing. You know that this is a positively charged particle. Okay, so we knew that just like Dirac had predicted, there was a positively charged particle called as positron. Okay? It turned out to have the same value of E and M as electron, except the charge was positive. Okay. Pauli had predicted a theory of neutrino, but Fermi developed the theory of beta decay using neutrino. Okay? So in fact, if you remember, the spectrum of beta of kinetic energy was shown to be like this. Okay? So Fermi at this point, this is a parallel theoretical development. Fermi actually showed that if you have a nucleus Z, go to nucleus Z prime with electron and this, now we know it antineutrino, at that time we did not, but just a neutrino. Then he showed that you can write down the number of particles at some given momentum in terms of various functions. So this was the density of states function. So this is like phase space. This is the matrix element, and this is some kind of shape factor that he called. The lesson is that not only did Pauli's postulate say that neutrino is produced and cannot be detected, Fermi's theory could actually also predict the shape of this kinetic energy spectrum and also the shape of electron momentum spectrum. And that gives you confidence that indeed what was missing in beta decay was actually perhaps the neutrino. Okay? Still, this is not the discovery of neutrino. I want to emphasize again and again, discovery will come later. Okay. So here we are in 1935, and what do we have? We essentially have electron and positron, we have proton, we have neutron, and we have nuclei. Okay, that's where we are at. Okay. Cosmic ray particles were of course being seen since 1912, since Hess did the experiments. Cosmic rays are primarily protons. They will hit the atmosphere. Atmosphere, of course, has nitrogen, oxygen, various other gases, and it will produce various other particles. It will produce just some nucleons. Some of them are pions. Pions decay to give muons and neutrino, and so on and so forth. So you get very large showers that come at the bottom. Okay, so when you come at the bottom, you actually get some photons, maybe some electrons, positrons, and some muons. So this was the time when on the theoretical front, Yukawa had given his meson hypothesis. So it was said that if the forces of nature are carried by particle exchanges, okay, but depending on the mass of the particle, the range of the force will change. So the particle was completely massless, the range would be infinite. The particle had mass m, the range of the force would be proportional to 1 over m. Now it was known that nuclear force had a range of a few Fermi, and that would correspond to particles of a mass about 100 MeV, around that order. Okay, so therefore people expected that there should be some subnuclear particles, which he called Yukawa's mesons, which should have mass of about 100 MeV. Okay. Now in cosmic ray particles, many particles were actually found which have similar masses, about 100 MeV or so. And therefore, it was expected that these would be the mesons of Yukawa that were expected to be. And turned out that actually were not mesons. They actually were muons, which we now know are actually leptons and not mesons. In fact, they were called at that time as mu mesons, but of course, the identification was wrong. TIFR was conceived and built by Homi Bhabha, as you know. Homi Bhabha worked on these particles a lot, and in fact, he was the one who, definitely among the first ones, who stated that these particles cannot be mesons. They have to be what he called as heavy electrons. And with the sparse data that he had, he said that this corresponds to a particle which is like an electron, but had a mass of a few hundred times the electron, okay, which we know actually right now is true. So he played a part in identifying this as muon as a heavy electron. This came as a surprise, and I think it was Rabi who made this famous statement, who ordered the muon, because everybody was quite happy to have found protons, neutrons, electrons. All the world that you see, is stable, and my atoms in my body and this room, everything is explained by using neutrons, electrons, protons, and nuclei. You really did not need this extra particle called as muon. So the question that was asked was, who ordered the muon? As we see, many things more were ordered, which are going to be on our menu very soon. Okay. So this was about 1936. So we are just going forward slowly in time. In about 1945 or so, experiments of Cecil Powell using nuclear emulsions actually gave you tracks that seem to come like this. I don't know if can you see this from the back. The track actually is very rarefied here. It becomes darker as you go here. At this point, suddenly it changes direction, becomes very, very light, and then starts getting dark. A track getting dark is a signal that the particle is slowing down, okay? Because you get more and more signals in nuclear emulsion. It interacts more and more. So this is a particle that came, which has slowed down, and at this point, it definitely decayed into two particles, one of which has gone this way. Other particle must have gone in some other direction, which you cannot detect. And this particle moved very fast, which means it had less energy than this, less mass than the particle which has now decayed. This has a very long range. Okay? So long range particle is muon, and this interaction is actually a pion coming in, slowing down in the emulsion, maybe stopping. At this point, it decays into a muon and a neutrino. You do not see the neutrino, but the muon is observed. Okay? So these tracks, this is of course a sample track, led to the discovery of the first meson. Maybe I should also say this, that before Powell, a few years before that, some of these signals were observed in experiments done by a few Indians, notably Biba Chowdhury and Dighe. Dighe and Bose, sorry. Dighe and Bose. But of course, their detectors or their emulsion did not have as much resolution to be able to separate these two. Okay, so there were some indications, but of course, Powell got the Nobel Prize for this, for discovering pion. Okay, so now we have our muon, which we identify as lepton, and we have a pion, which we identify as a meson. Okay, and these two particles, as you know, play a large role in identification of any particle which is heavier than this. Okay, we are going to move back and forth between theory and experiments. So this was the time when Feynman's finger Tomonaga came up with the theory of QED, or the quantum theory of electrodynamics, and which, just like what Yukawa had said, they said that charged particles will interact by exchange of photons. So if you have E plus and E minus, the E plus will give a photon, it will be absorbed by the E minus. Sorry, this is both are E minus, sorry. And then as a result of this photon exchange is what you see in electrodynamics. Okay, so this was the principle of electrodynamics that came around 1950s, so around the same time. Particles were being discovered about which were not expected or predicted by theory. And one of them, which again forms a very large part of what we do today, are the strange particles or the kaons. Okay? These were found in these bubble chambers by Butler and Rochester in Brookhaven. And of course, this is exactly like what we see in LSC, right? LSC perhaps has a large number of tracks, but this is at least something where you can see very slowly. Of course, this is a very wisely chosen photograph, and that's the reason that this is true. You see that, so this is, I think this is lead, if I'm not wrong. You can see this V shape here. Okay, a V shape which does not touch this. Okay, which tells you that there was something which was traveling here, which was a neutral particle, which has decayed into two charged particles. These two charged particles are identified as pions, and therefore this was a neutral particle which has decayed to two pions. And that tells you that if you, of course, you do as you usually do, you measure out of such particles, find the invariant mass. It turns out that they have the same invariant mass, around 500 MeV, and that is the discovery of K0, neutral K0. Okay, so this is the famous slide which tells you that. Here, ignore all of this. Look at this point. This is a particle coming from top. At this point, it changes its direction, and another particle goes like this. Okay? This is a very large, long-range particle. This can be identified to be a muon, but this is a charged particle that came, decayed to muon and something else. And then, by again looking at many such slides, you figure out that this particle also has a mass about 500 MeV or so. And this is the sort of the slide to show that this was a K plus. Of course, they were given the name stage particles because of their larger than expected lifetime and the fact that stage particles came in pairs. So, but we will not go into that. Okay. So now we have muons, pions, and kaons after 1935. We had found positron, if you remember, but we had not yet found antiproton. If you want to antimatter, to prove Dirac's contention that for every particle there is an antiparticle, okay, we have shown that for electron there is a positron, but we should also be able to show that for a proton there is antiproton. This in particular was shown in an experiment by Chamberlain and Segre in 1955. So this is the event which is commonly or popularly called as the star event, because whatever antiproton the particle did not know actually came, hits here and forms many charged particles. You find out the total charge of these particles, ends up that that this particle should have a charge of -1. There was also another experiment in which you saw the particle bending, and it bent in the right direction to show that this particle was negatively charged and not positively charged like a proton. And this confirms that this was an antiproton. So in 1955, we sort of knew for sure that for almost every particle, there is going to be an antiparticle, at least for the particles that we know in our nature. So cosmic rays and accelerators that were built at that time were, of course, a large source of new particles, and the particles kept on being discovered. So earlier we had a very long time between electron and proton, but now you see, once we had neutron, positron, muon, pi, and k, suddenly a plethora of all particles were discovered in the 1960s and 1970s. Okay. So this became a zoo of particles. People try to find their property. Okay. But of course, we are in some sense reductionist people. We want to understand properties of everything in terms of properties of a small number of particles. Okay. And therefore, attempts were made try to understand all of these in terms of smaller constituents. Okay. And in fact, it turns out, at least now we know, that all of these particles can be explained by combinations of more fundamental particles, which of course we now know as quarks. So these will be described by up, down, and stage quarks and their anti-quarks. How do we know this? We have to find some patterns in these objects. So although they look like many stage particles, perhaps some patterns exist. So the theorists tried to look at such patterns, the patterns in masses, lifetimes, properties, and so on and so on. With those patterns, then you group particles that seem to be having similar properties. Okay. So for example, these are two of the patterns that were found. This is what Genman called as the eightfold way. So this is a set of particles which have similar properties. These are all light particles. All are pseudoscalar mesons. These two have stageness of -1. These are stages of +1, and these are pions. This is what is called as a meson octet. There's a very similar octet of another 8 particles, in which you don't have pseudoscalar particles but vector particles. Okay, so instead of K, you have K star. Instead of pi, you have rho, and instead of eta, you are going to have phi. So this told you that there is some pattern. You also found a similar octet in the case of baryons. Neutron and proton form a part of the octet, but you also have other particles like lambda and sigma and cascade. Properties of these particles could be understood in terms of, as I said, U, D, and S quarks. If you go some time ahead, you can figure out that indeed all of these particles, all of the mesons are simply formed by a quark and antiquark, and all the baryons are simply formed by combinations of 3 quarks. Okay? And all possible combinations are the ones that end up giving us this octet. Okay. So far it's so good. So we have now managed to find a pattern in the mesons and baryons, the particles that we have kept on discovering. One nice pattern that was found later was the pattern for decuplet of baryon. Okay. Theory also tells you that if indeed your symmetry is what's called as SU3 flavor symmetry, then you would get 2 octets of mesons. And for baryons, you get 1 octet and 1 decuplet. Decuplet simply means a set of 10 particles. Okay. The above 9 particles actually were found. Okay. So these 4 particles are called as delta, delta minus, delta 0, delta plus, delta plus plus. And we of course know that they are formed by only up and down quarks. Then we have 3 sigma particles, which are formed with 1 strange quark, and we have 2 cascade particles, which essentially involve 2 strange quarks each. This was the last particle to be found, but it was expected that no, since we have U here, this is up, 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 down, 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 we'll perhaps also get the stage particle. This of course creates a problem in people who follow the Fermi, who say that, and Pauli, who said that there is a Pauli exclusion principle for fermions. More than 2 fermions cannot occupy the same place at the same time. 2 you understand because 1 can be spin up, 1 can be spin down, but 3 particles is not possible, right? So you cannot have UUU or DDD or SSS in the same nucleus. On the other hand, you definitely have found delta plus plus, you definitely have found delta minus, and well, you perhaps will find this SSS. Okay? This is what led Gelman to propose the idea that the antisymmetry that you need for fermion wave functions, which is not available in just this, is given by another quantum number called as color, and the 3 quarks that you see are actually have different, this is just name given as colors, and you can antisymmetrize over the colors and be safe. The wave function will be antisymmetric. We will talk about this color more tomorrow when we talk about theoretical ideas behind exactly what this is. Okay, I just want to put this in perspective. So around 1960s, we also knew that the colors could explain existence of UUU, DDD, and SSS. See, we are making patterns, and if we make predictions for particles that don't exist, that gives more credibility to our patterns, right? Similar to the fact that we discovered, many of you must be present in collaboration that discovered top quark in 1995, right? That was the missing place in the pattern. To complete the pattern of standard model, you need a top quark. So similarly, to complete the pattern of this decuplet, you needed discovery of this omega minus, which was the next step in the discoveries of these particles, which were discovered in 1964 in Brookhaven. This is just a very beautiful diagram, and I simply like to see it. It's there in a book like Griffiths. You will find this. So don't ignore the figure and go ahead. Try to understand exactly what's happening each of these vertex. It's just so nice. This is kaon coming, hits the proton, which you don't see here, produces 2 other kaons, which is K0 goes here, doesn't leave a track because it's neutral particle. This is K plus, which turns towards left. This omega minus charge particle leaves a small track, decays to sigma, pi minus, which bends. You can see this. Sigma you cannot see because it's neutral. It goes to lambda, which you cannot see, and a pion cannot see. But pion goes to gamma gamma. This is lambda. Lambda goes to p and pi, and so on and so forth. Okay, it's studying of this event tells you a lot about particle physics and how you can identify particles in a detector. Okay. Now, of course, I guess we have particle finding algorithm. What are they called? PID algorithms, right? Particle identification algorithms, which do it electronically. But I think there is no, as students, I think it is very important for us to understand how this can be done in a simple way just by looking at how particles decay. You might be able to better the algorithm that we exist currently. Okay, so what do we have now? We figured out that quarks have maybe come in 3 colors, and these 3 colors, as again we'll see tomorrow, actually correspond to interactions between quarks, which are called as strong interactions. So this theory of strong interactions is called as quantum chromodynamics, where chromo, of course, stands for colors, and that's how at least linguistically it connects. So these quarks interact via exchange of gluons. Another discovery that came out of nowhere, unexpected, was the discovery of parity violation. Again, we will look at the theory of this in detail tomorrow, but the fact that parity may be violated in interactions was predicted by Li and Yang in 1956, and experiments of Madame Wu and later those of Lederman and Telegdi in 1957 showed that indeed parity is violated, which means that interactions, especially weak interactions, can actually be either left-handed or right-handed. Okay? You can look at an interaction in the mirror, and you can identify which one of them is real world and which is not. Okay, so we know it is indeed violated, and we'll talk about it tomorrow. Whether it was observed as parity is violated, in fact, that also was indication that weak interactions have a handedness. It was expected that maybe charge parity will not be violated, okay, because the experiment that were done actually showed that it's possible to have conserved charge parity. But again, everything that theories think is not the way nature behaves, and that is job of experimentalists to show theories that what they think is not always correct. That job was done. This job was done by Cronin, Frisch, and Christensen in 1964 in experiments that had to do with kaons. We will again look at this experiment in detail tomorrow. Okay, so this is about 1964. Combining all this experiment that we have now, finally came the theory of electric interactions by Glashow, Salam, and Weinberg. Okay. Somewhere here in the middle, I forgot to write it down, came the intermediate step, which showed that weak interactions are what are called as V minus A interactions. So the left-hand interactions. And that was, as is popularly called, it was first proposed by Sudarshan and Mashak, but was popularized by Feynman and Gendon. Okay. Good. So now we are in 1970. Okay. I would like to stop in 1970. Well, one reason is it happens to be my birth year, but also because this is the time at which we have a slightly clearer picture of the Standard Model. Okay. So you have what we now know as the first generation of quarks and leptons. We had neutrinos and neutrino discoveries. I'll come to sometime later, but we had this in 1970. Before that, we had stage quark, and these 3 quarks, if you remember, made up for this our baryon decuplets and meson octets. Okay, we of course knew photon, which was the force carrier of electromagnetic force. Fermi theory actually gave rise to, so we actually knew that for strong and weak nuclear force, there will be intermediate particles, force-carrying particles like gluons, W and Z. But at this point in 1970, they have not been discovered. Therefore, these three places are still empty. We have no clue that there is anything like third generation, right? I mean, I took this because I took a figure from some place and I rubbed out these white parts. But of course, at that point, people were very happy with even saying this. It wasn't even clear that there'll be something here, okay? Because all you have done is found these three quarks, and these three seem to be actually forming some kind of a triplet because they form your octet and decuplet. So there was, at this point, initially, no reason to suspect that there is something here. Except for the fact that you do experiments, try to make precision measurements, and then you find something that doesn't really fit. Okay? And that was found by Glashow, Iliapoulos, Mayani. Well, it wasn't found by them, they had to explain this. Observation was also experimental, which was to explain the decays of K mesons. Okay? So you looked at K plus going to mu nu and K long going to mu mu, and you find that K long to mu mu actually doesn't even happen. Nothing was seen. Naively, you would expect these two to be related and have sort of similar branching fractions, but it was not happening. The reason for this was proposed by the guys called Jim. It's called a Jim mechanism, who showed that if there is this quark called as charm quark, which sort of fits in here, and the charm quark also mixes with the S quark, the charm quark mixes with the U quark, then it turns out that in the neutral K or decay, the amplitudes will cancel, and therefore you will not see the decay of K long going to mu. So the existence of charm quark was postulated and through this mechanism, and as an explanation, it was taken seriously. But again, that is not a discovery.
Before that, in big industry scattering, the partons were postulated.
Partons are postulated, yes. The postulated is true. Yes, I missed that, yes. But discovered, no. Well, I'll come to discovery of partons. Okay. However, so this was just postulation. The discovery came when you saw an experiment in Richter and Ting, experiment with E plus E minus colliding. Okay, and which gave you a peak. So at a value of about 3.1 GeV, okay, which is a mass of J psi, okay, which is again made up of E plus and E minus. Okay, so this is the plot. This is the mass of E plus E minus, outcoming E plus E minus, which was plotted, and this is the peak that you saw at 3.1. The same technique that we keep on using even now. Try to look for peaks of the particle masses, invariant masses of particles. So this is invariant mass of E plus E minus pair that is coming out. So this peak is 3.1, is approximately coming out at 2 times the mass of the charm quark. So now we have a charm quark at mass of about 1.5 GeV, and our first 2 generations are now complete. Okay. There is still no clue of third generation. Okay. However, there is this lingering problem of CP violation, okay, which we know exists, and Kobayashi and Maskawa, who were trying to explain the charge parity violation and the 2 generations, tried to give a simple solution by saying that if we had a third generation, we could explain it very easily. Okay, and so it turned out that this actually happens to be the real reason, because this is going to explain hundreds of different observations. After those hundreds, at least 10 of them we will see in our third lecture, okay, to see what are these things that explain the charge parity violation. Okay, so at this point, remember, third generation has not been discovered yet, but we know that if it exists, we will have a solution of charge parity violation. This is 1972. Not so soon after, okay, in fact, soon after. So in 1975 came the first third generation particle. Okay, 3G is third generation particle, which was tau lepton. Okay. So how was tau discovered? Okay. You looked at E plus E minus collisions, okay, and looked for events where you get E minus and a mu plus. Now, clearly, you don't produce E minus and mu plus from a single vertex. Okay. So, in order for that to happen, this E minus must have come from some decay, and the mu plus must also have come from some decay. Okay. So, this tells you that this is the interaction where, and remember, everything else is neutrino, so nothing else is seen. Okay. So, this is again a very clean event with very small background where you get E plus E minus colliding, but outgoing particles are E minus mu plus, okay, which is the one that you see here. This is a track. These four things that you see are the four vertices which have been tracked along. So now we had one more particle called tau in the third generation, okay, about 1975. The first quark in the third generation, which is bottom quark, was discovered very soon by Lederman, who had very famously missed the earlier CEPSI. E plus E minus goes to epsilon, which is BB bar. And therefore, if you look at E plus E minus invariant mass, it's coming out. Again, this is the background. On top of the background, you see this nice peak. This peak is around between 9 and 10 GeV, and therefore would correspond to twice the mass of MB. Okay. So this tells you that there is another particle of mass about 5 GeV or so, which now we know as a bottom quark, or also called the beauty quark. Okay. Remember, we said that we knew that there are force carriers of strong and weak interactions, but they haven't been seen yet. Okay, so till that time, this is only postulation. Gluon, which is the carrier of strong force, was discovered at DAISY in the Petra ring experiment called as TASO, which is a 2-arm spectrometer solenoid. And the kind of event that was seen was, so E plus E minus collided here, and you see, so this is transverse plane. Okay? So is E plus E minus collide like this, and what I show you is the picture in this plane. You saw 3 jets here, here, and here. And only way to explain these jets, because they're odd in number, you cannot have, if it was QQ bar, then QQ bar would have been 4 jets, right? But you actually see only 3 jets, and that tells you that one of the jets must belong to a gluon. And this was the famous 3-jet event in 1979, an iconic event among many others, which shows you that indeed the gluon, which is a carrier of strong force, also exists. Okay, so this is the discovery of the strong force. Okay. The experiments were built especially to find the weak force, thanks to Vandermeer and Rubia. Vandermeer was, of course, a great instrumentation person. I think we should mention it especially here. Go ahead.
Daniel was in the experiment. He was also there in that.
Oh, okay. So, yeah. So these are again iconic figures in which the W and Z were actually discovered. That's what we call discovery. Again, let me point you out what the event that we have seen. So this is a mu plus. This is a mu minus. Long-lived particles, long-range particles. Find the invariant mass, and you find the mass of Z. Okay? So this was the discovery of Z with mu plus mu minus. In this particular event, you will perhaps see, I hope that I have a clear slide here. You perhaps see a muon that goes from here all the way, and that was a muon coming from the decay of a W beta. Okay? So of course, all of us know that one picture says you nothing, right? One picture is just a picture to show something, illustrate something. You need to have thousands of those pictures. Many of them are going to be backgrounds. And one of our jobs as experimentalists is to throw away those backgrounds and statistically find that some of these are signal events. It's almost impossible in any experiments to show one picture and say, this is what I saw. Okay. So when I show you this, although invariant mass of this could be equal to 90 GeV, it's not a guarantee that this has to be a Z. Okay. There could be background because of other events, and this will when you take the statistics, you will perhaps find a peak coming candlestick value. So that is just to give a caveat. Although I show some nice pictures, they just because they can be shown for illustration. That's something always to be kept in mind. Govindo should also tell me how much time I have. So
I was just waiting for 6 minutes.
okay. Sorry. Yeah. Okay. I forget if I have it in the slides. I perhaps might have it, but maybe not. It goes in my neutrino. No, I don't have it. Okay. Okay. So I have 6 minutes left. So we will now jump. Okay. So 83, we come to 1995, discovery of top quark. And I know many of the people here in the audience were part of D0 when it was discovered. I actually also happened to be in the hall when the discovery was announced. I was a graduate student, although doing some theory. So this was a PP bar collisions, and which produced a top bar pair, and finally giving you top goes to a B jet, and you also get a muon here. On the other side, you got these 3 jet events. And of course, now we go further, things become more and more complicated. So here, so now we have finished all our particles. We have 3 generations of quarks. I told you about these 3 leptons. I will just very quickly tell you also about the 3 neutrinos. But we also have these 4 force-carrying particles. Okay. Neutrinos come separately because they are difficult to detect at accelerators. They have very weak interactions. Therefore, they escape very easily. And therefore, the discoveries are not at accelerator experiment like the other experiments were. Okay. But of course, we know there are 3 kinds of neutrinos: electron, muon, and tau. What's an electron neutrino? They are defined in a reverse way. If a neutrino produces electron after colliding, let's say, with a nucleus, it's called electron neutrino. If it produces muon, it's called muon neutrino. If it produces tau, it's called tau neutrino. Okay, so the flavor of neutrino is defined by what it produces, what charge particle it produces after it interacts with something. Okay. Just to complete the story, Pauli postulated neutrino in 1930, but it took 1956 by the time the neutrino was actually discovered. Okay. And in 1995 till it got a Nobel Prize. Okay. This was again a very, very clever experiment. This is a different kind of experiment than normally we have an accelerator. So therefore, just I come to explain this. This was next to a nuclear power plant, which made antineutrinos. Neutrinos come in, hit, let's say, a proton, and they produce a neutron and a positron. Okay. Now, this positron slows down, gets absorbed, and produces annihilates with an electron and produces a pair of photons. This neutron keeps on scattering inside this scintillation material. This has cadmium chloride. Cadmium is a good neutron absorber. It absorbs the neutron and gives out a gamma ray photon. Okay. Neutron takes some time to travel. So this is a slightly delayed signal as compared to the 2 gamma signal that is given by this. Okay. But again, you have a 3 photon signal, 2 photons almost simultaneously, and 1 photon coming after a delay, which was the signal for electron neutrino. Okay. Muon neutrino was a different and strange story. Muon neutrino, nobody thought they would be a muon neutrino. They wanted to see the neutrino, electron neutrino, but in the decay of muons that come from accelerators. Okay. So this was the accelerator from which you created a pi beams. Pion decayed to muons. Okay, and there would be a neutrino coming out. Okay. So it was not known that is a muon neutrino. So it was expected simply to be the same neutrino that came out in beta decay. And we knew that a neutrino coming out of beta decay produces electron, okay, or positron. It was expected that what you will get in this detector or this spark chamber are mainly electrons. Okay. Turns out that the experiment failed and it did not find a single electron. On the other hand, it found some 27 muons. Okay. So instead of electron, what you had produced was muons, and this indeed was an indication that this neutrino was different from a neutrino which was produced in nuclear reactors, which produced electrons. So remember here, you had positrons produced, okay, not muons. But decays of pions seem to be producing muons, and that tells you that this neutrino actually was a muon neutrino. Okay. So this was discovery of the second neutrino, for which Lederman, Schwarz, Steinberger got the Nobel even before the first neutrino got its Nobel Prize, which happened quite later. So those results, of course, are interesting but different. Yeah. Discovery of third neutrino happened in a sort of very nobody really cared, because everybody was so sure that all the three standard model generations have been discovered. People knew that nu tau will be discovered at some point or the other. So it almost went unnoticed, the people who were not involved. But this was, of course, a very creative experiment called Donut in Fermilab. This is a nuclear emulsion detector. This is a small size. You see the scale is here. This is millimeter scale. This is 1 millimeter from here to here. All of these are nuclear emulsion panels. This was a beam of neutrinos. At some point, it produces tau neutrinos, which decay, and you look at the products of this tau neutrino decay, which finally tell you that this indeed was a tau neutrino. Okay, so our standard model is now almost complete, and really we don't need to go beyond this, okay? Except for this nice theoretical nugget that says that you can do all of these things. But if we believe that interactions, the strong, weak, and electromagnetic are the way that we understand them, which means they are gauge theories. Again, we'll talk about it in detail tomorrow. Sure.
Three kinds of neutrinos that you're using for the experiment. If the source is different for all the three cases, I'm just trying to understand if the properties of neutrino are different, or is the target that produces different?
No. So a neutrino is created along with an electron, will be an electron neutrino. So in the case of the sun, for example, okay, this neutrino is produced at the same time as an electron is produced. So therefore, this is electron neutrino. So any neutrino which is involved in interaction with electron is called electron neutrino. Now in the atmosphere, for example, okay, you can produce muon neutrino at the same time as you produce a muon. So neutrino which is produced with a muon will be a muon neutrino. Okay, so production mechanism of neutrinos of these flavors will be different. Each of the time they will be produced in conjunction with a different lepton, an electron or a muon or a tau.
And so that my question was like, when you are doing this controlled experiment, so the source was different for neutrinos?
Yes. So yes. So for example, for electron neutrinos, the first experiment, the source used was reactor. Nuclear reactor which produces only electron neutrinos. Now we know them to be antineutrinos. For the muon neutrino, the source was pions. So you accelerate particles, have a target. To hit the target, produce a beam of pions. Now pions, when they decay, almost 100% of time they produce muon neutrino, and so on. Okay. So as I said, there was this theory Nigel. This is almost my last slide. Yes? This theory Nigel, which said that if you have this strong, weak electromagnetic interactions, and if they're indeed true gauge symmetries, all of these particles that you see here, this what 12, right? Yeah, no, okay, 16 particles. All of them have to be massless. Okay, so you cannot produce particles which have mass, but which also interact the way that we expect them to. To resolve that, we needed something else. The mechanism that was proposed for that was the Higgs mechanism, which also predicted Higgs boson. Okay, so again, till we saw the Higgs boson, we will not be sure that indeed this was the mechanism. But as we know, about 10 years ago, we did discover the Higgs boson. This is the Higgs boson discovery picture for Atlas. This was Higgs to ZZ star. So with 4 leptons, these are the 4 leptons that you see, red, red, blue, blue, coming out. At CMS, this is one of the CMS, again, randomly chosen events. Okay, both of the experiments actually discovered events of both types. I've just chosen representative pictures. This is a gamma, this is a gamma, this gamma, Higgs to gamma, gamma event. You reproduce invariant mass and you get Higgs. Okay. So 1912, now we had the Higgs, and that completes the standard model. Okay. So this is the time to stop. So remind you, this is where we are. Tomorrow we'll go to theory, and third lecture we will go to how to test this in this. So let me start. Thank you, Amol.
Any question? The speakers? Don't be shy. Irene, we'll have a tea break.
There's one here.
So, when you talked about the discovery of W boson and Z boson, so you told that it decayed into mu and neutrino. So did we actually measure the neutrino mass also to find out the invariant mass, because that is very
No. So see, in any accelerator experiment, neutrinos is very difficult to measure because neutrinos just escape the detector. Detector is not large enough to produce. So neutrino experiments are large in size. So you have to look at a statistical distribution of the energy of this mu coming out. Okay, and that will tell you what is the mass of W boson. Daniel is here, so you could correct me if I'm wrong.
So you measure the tail end and you estimate that this is the mass of W boson.
Yes. So we'll measure the spectrum. Tail end as usual is very difficult to measure, but you know what the shape is because we can predict that. So if a W decays, what fraction of energy will go to lepton and what will go to neutrino, and based on that shape you fit to find the value of W mass. Okay. So again, other people here are better in the position to answer the question. So.
Thank you, sir. You discussed about the cosmic rays dark matter in the standard model. What is the principle of production of neutrinos emissions? Because as I have studied, the neutrinos does not emit regularly from the galactic and extragalactic sources.
Could you repeat that? Sorry.
How the neutrinos are produced in the galactic and extragalactic sources?
Okay. So the main way in which neutrinos are produced are actually decays of pions and muons. So there are particles are accelerated to large energies, let's say even inside stars. Okay. These accelerated particles hit other particles around that. Okay. So just like cosmic rays hit the upper atmosphere and produce pions, even in the other galaxies or stars, you will produce pions through some nuclear interaction. The main source of neutrinos that we get on Earth from the outside of the galaxies, okay, is through the decays of these pions. The pions decay to the muon neutrino, and these neutrinos come to us.
Will there be any contribution of X-ray and gamma ray in the production of neutrinos? The contribution of X-ray and gamma ray for the production of neutrinos?
Okay. Directly, no, because neutrinos don't interact with photons. Okay, so there is no contribution of gamma rays as such. However, what happens is whenever you have a source that gives neutrinos, you also get gamma rays. The reason is that neutrinos come from decays of pi plus and pi minus. Okay, gamma rays very often can also come from decays of pi zero. Okay, so same interactions that produce pi plus pi minus will also produce pi zero, therefore produce gamma rays. So very often the neutrinos come in conjunction with gamma rays because you produce pi plus pi minus pi zero. Pi zeros will give you photons, and pi plus pi minus will give you neutrinos, which come here.
Will there be any?
Stop with the here and the tea table we will have a full discussion on it. So if you have a shortage of time, we'll
Thank you,
have a
sir.
break for the 20 to 25 minutes, and 11:50 we will come back here for the next talk on the detector by Daniel. Just one thing I said that in this lecture, if you can see the front page of your notebook, you will see an excellent picture of the bubble chamber. That's for this is the event where all these things are clearly seen. Yeah, so we'll come back at 11:15 here for the next.